So these are the courses, and now you're showing the research activities here, right?
Yes, yes. And one Professor Bhina Sajawal, you know her also. She will also join today.
Who?
Professor Bhina Sajawal, UNSW, Australia.
Okay.
She mailed me that I want to
I know
join.
her name. I know her name, and I think she was also an IIT Kharagpur alumni, right? Or maybe not. I'm not.
No.
Okay.
These are our research area.
Mm-hmm. You cover pretty much all of the areas, at least in metals materials, right?
Yes.
So how many graduate PhD students you have?
Professor Asthana Ghosh.
Oh, hello, Dr. Ghosh.
How are you?
Yeah, I'm doing fine. Thank you. It was good to touch bases with you by email.
Yeah. And thank you very much for being with us in today's program. We're really glad to have you in this program.
You're very welcome. I'm happy to be here.
So you are asking about students.
Right.
So presently there are about 24 PhD scholars who are doing.
Okay. And how do you support them? Like you have fellowships, or I know CIR and those organizations, they used to offer fellowship opportunities, right? How do you support graduate students?
Mostly they are getting the institute fellowship, that is from MHRD. They are getting this fellowship, and some students are enrolled under some specific projects, and they're getting the fellowship from that project grant. Okay. Mostly the institute scholars, and two, three are in TCube. They're getting fellowship from TEQIP. That is the Technical Education Quality Improvement Program.
Okay.
So that is the thing.
Okay.
So what is the local time now? Your place?
Sorry?
Your local time now?
Right now it is, let's see, it's 5:24 in the morning.
Okay.
And yeah, right now it is pretty dark outside, and we have all the snow.
Yes.
So it started snowing about a month ago.
Mm-hmm. So how's the COVID situation now there?
It's not really good. It's pretty much the same like everywhere else. So we have had some increases, spikes in different areas. I live here in Wisconsin in the Midwest region, and our area is not very heavily populated. So, and also because the universities mostly they went online, or at least in the hybrid mode, where you have some in-person collaboration like labs and all, and the rest is online. So that has kind of minimized exposure to the pandemic. But yeah, things are not good. But vaccination just started, I think, here and India also, I think.
No, it will be starting. It will be starting from the next week. I just gone through the news. It's likely to be started from the next week. It will begin with the different person and the doctors and the nursing staffs.
Right.
So it is likely to be started from the next week.
Okay. It will take a few months before I think everyone is vaccinated, I guess.
Yeah.
Yeah.
And this place in India is highly populated, so it may take you get maybe several months it will require to reach it to us.
Mm-hmm.
So 3 minutes, I think 3 minutes left. So Arup, also
Yes, yes. Yes, sir.
So
2 minutes
start,
remaining.
2 minutes of starting time, so that. So Professor Asthana, what platform are you using in your institute? Online teaching?
We use actually the same Teams and to an extent also Google Meet.
Okay.
And FaceTime is also used, but that's mostly for like social interactions. So I would say Google Meet and Teams.
Okay.
And for posting content online, video lectures and all, we use Kaltura Capture. And
Okay.
the platform is actually Canvas.
Okay. So your Google Meet, there's Microsoft Teams, so I think.
A little bit. Yeah.
Yes, Robin.
Sorry?
Yes, sir.
Robin? Yes.
Am I audible, sir?
Yes.
So, sir, can I start? Or
Yeah,
1 minute left?
1 minute, because our social media broadcasting will not be activated until 5 p.m. because the time setting as 5, it will start from 5 p.m. Then just I think 10 seconds, 10, 20 seconds. Yes, you can start.
Okay. My greetings to one and all. Welcome everyone to the 5th as well as last webinar of the ongoing webinar series organized by Department of Metallurgical and Materials Engineering, NIT Durgapur, with Association Institute of Metals, NIT Durgapur Students Chapter. Before moving ahead, I urge the attendees to kindly mute themselves and switch off their cameras for smooth running of the event. We know learning never stops, so does discovering. Keeping in with this view, the newly inducted students chapter of NIT Durgapur is enthralled to begin its journey, striking the right chords with this series of webinar. And we are pleased to have Dr. Rajiv Asthana encouraging us today in our effort. Without any further ado, I'd request Dr. Madan Mohan Ghosh, head of the Department of Metallurgical and Materials Engineering, to speak a few words to our guest.
Sir, unmute.
Sir, please unmute yourself.
Sorry. Thank you, Robin. Respected speakers and their participants, a warm and hearty welcome to this online interaction session. We are happy to have Professor Rajiv Asthana of University of Wisconsin Stout, USA, as a speaker in today's online lecture. This program is the fifth of the series of webinars organized jointly by our department and the newly formed Indian Institute of Metal Students chapter here at NIT Durgapur. I would thank our institute authorities and IIM officials for extending their support to organize this kind of programs. And of course, my heartfelt thanks to my colleague, Dr. Arup Kumar, for his support as the faculty advisor of IIM Students chapter to organize such kind of programs. This type of interaction programs and functions will enlighten our department and our institute as a whole. Interaction between academic institutes, research organizations, industries is of utmost importance to achieve excellence in engineering education. The Department of Metallurgical and Materials Engineering of National Institute of Technology is really privileged today to interact with Professor Asthana, who is an eminent professor and researcher in the field of metallurgy and materials. On behalf of our department and on my personal behalf, I express a warm and hearty welcome to Professor Asthana in this online interaction program. Our department has organized several courses, seminars, workshops, etc., with speakers from academic institutes, research labs, and industries all around the globe during the last 2 years. And during the present COVID situation, the department is organizing webinars in this form almost in a regular basis. The today's webinar is jointly organized by our department and the IIM Students chapter at our institute. I can see an overwhelming response from the participants on today's program. I hope this webinar will be extremely beneficial to the participants, and the participants will surely enhance their knowledge base in this area. We are thankful to Professor Asthana for being with us through this virtual meeting platform as a speaker in this webinar instead of his very busy schedule. I am sure this interaction program will be a platform for initiation of research collaboration and network formation between the two academic institutes. I hope all the participants will enjoy this interaction program, and I wish all success of this program. Thank you all.
Thank you so much for your enchanting words and being tender towards us. Let's now move on to our today's technical session. We are extremely glad and grateful to have Professor Rajiv Asthana to grace the occasion with his presence. The topic of his today's technical talk is ceramic integration using active brazing and diffusion bonding. Before starting the technical session, let me introduce to our honorable guest speaker to everyone. Dr. Rajiv Asthana is currently in the well-distinguished position of professor at the Robert S. Sarbenka School of Engineering, University of Wisconsin Stout, USA. He did his bachelor's and master's degree in material science from IIT Kharagpur, and he did his doctorate from University of Wisconsin, Milwaukee. He is teaching in UW Stout from 1995 till now. He also worked in NASA Glenn Research Center as a scientist and also worked at Advanced Materials and Process Research Institute or CSIR AMPRI, and also as a CSU postdoctoral research associate. He had a visiting professor at University of Wisconsin Milwaukee and a visiting scientist at Polish Foundry Research Institute. He was George Baker Memorial Matter from 1988 to 1999. Sir has been awarded Distinguished Engineering Educator Award, UW Milwaukee Dean's Outstanding Alumni Award, Department Alumni of the Year Award, and a lot more. He also has been a fellow of ASM and ASM IIM lecture. Famous books like Engineering Materials and Process of Disk Reference, Materials Processing and Manufacturing Science, Solidification Processing of Reinforcement Metals, Atlas of Cast MMC Structure, etc. are enriched by Professor as an author. Recently, Sir has been working on mainly active metal brazing of graphite foam, titanium joint, and silicon carbon ceramics, and also TEM of interfaces in diffusion bonded and silicon carbon fiber bonded ceramics using titanium copper interlayers. It is impossible to describe his contribution to the field of material science and engineering through his research work. So without any further delay, I would like to invite Dr. Rajiv Asthana to share his precious knowledge with the attendees.
Thank you very much for the introduction. I'm glad to be here, and I'm especially happy that we have several students also attending the talk through IIM student chapter. Let's see if I'm able to share the content here. All right, can you see this again?
Yes, sir, it's visible.
All right. So again, my thanks to Dr. Ghosh for this opportunity and Dr. Mandal for initiating this. And I'm going to look at some work I have been doing collaboratively with people outside my university. Mostly I'm going to look at integration of ceramics using active brazing. I was going to look at also diffusion bonding, something that we did for silicon carbide ceramics, but I believe I might run over the time, so I skipped that part. And please interrupt me with questions if you have any during the talk. And also, if I exceed my time, please let me know. So I teach at the University of Wisconsin South. We don't have a materials program, but I teach in manufacturing engineering and mechanical engineering areas. I teach mostly materials and manufacturing courses. These are the pictures of the campus, aerial views of our campus during summer. Right now, the lake is frozen, and you will see only white snow all over. Anyway, coming back to the topic, the work that I'm presenting here was done collaboratively with mainly two people, and I would like to acknowledge their contribution here. Dr. Natalia Sobchak, she is the department head at the Institute of Metallurgy and Material Science at Polish Academy of Sciences in Krakow. So, work on wetting of ceramics by high temperature alloys that I'm going to show here was done collaboratively with her. And the work, more applied work on joining was done jointly with Dr. Mrityunjay Singh. He is the scientist at Ohio Aerospace Institute, which is a part of NASA Glad Research Center in Cleveland, Ohio. So with that, let us go back to some of the basics. So first of all, why we want to study ceramic metal interactions. And this is something that our students will be knowing well. We have interactions between ceramics and metals at high temperatures in many different applications. Melting and casting technology, crucibles, furnace lining, investment casting molds, ceramic filters, all of those areas involve interactions at high temperatures. Composite materials, ceramics, we have high temperature interactions between things like graphite fibers and metal matrices, brazing and diffusion bonding. And this is an area that I'm currently involved with a little bit. And also in sintering, especially with liquid phase sintering of ceramic composites and crystal growth. So this is again not a complete list, but just gives a snapshot of the importance of interactions between ceramics and metals. Images of common metal matrix composites that show how interactions reaction can occur. So you have silicon carbide fibers in titanium, and you can see a reaction zone around the silicon carbide fibers. I think I'm missing the magnification bars here, but these are SCS fibers with a tungsten core and silicon carbide deposit outside. These are particulate composites at low and high magnifications, tungsten carbide, cobalt, cermets, which is also kind of a composite materials. And of course, in joining using brazing or diffusion bonding, we have interactions between brazed material and the substrate that you're joining. And at high magnifications, you will actually see different chemical interactions. So my interest has been mostly in these areas of joining. We looked at joining of core or another low expansion metals and alloys with silicon carbide. The application was for a fuel injector for NASA's micro electromechanical system. So fuel and air are basically mixed like in any standard injector, and the core tubes had to be bonded to silicon carbide discs here. Heat exchanger elements. We were looking at bonding titanium tubes to carbon foam sandwiched with carbon-carbon composite, high conductivity carbon-carbon composite. So the idea was for a fluid to titanium tube and dissipate heat to high conductivity materials around it. This is planar solid oxide fuel cells, where we looked at joining of yttria stabilized zirconia to steel using different types of brazes. We characterized the microstructure and other sealant properties. With silicon nitride and Inconel system, and we will see a little bit of that today. In that system, we were looking at joining silicon nitride ceramics to Inconel for these kind of turbine rotor applications. And also we looked at some ultra high temperature ceramics, like zirconium diboride based ceramics materials joined to different materials for pretty high temperature applications. Also silicon carbide composite. So our work was mostly confined to lab scale work, not really at the pilot scale, but we were looking more at the basic science level in all these systems. So just as an introduction to brazing process, especially if students are not familiar with it, basically you have some sort of a bonding material like a glue, which is a metallic braid, or it could be a glassy material. And these are the surface to be bonded. So basically you will melt the braid material, apply a small pressure, and let the system cool until you have a good bond. So the two main challenges in this kind of an approach are that the braze should be able to spread out on the surface that you're trying to bond, which means you have to have good wettability in the system. And secondly, there should not be excessive residual stresses that might cause fracture after the bonding process is completed. So the compatibility of expansion properties is important, and also the spreading behavior is important. These factors, especially stress and wettability, become really important for ceramic joint to metals. When you have metal to metal bonding, especially in a system like a turbofan engine, these challenges are less critical because you're using metallic brazes to join metallic components. You're joining nickel-based superalloys or titanium or steel components in the lower temperature side. So the expansion properties are not very different, and also the wetting is quite good. That is not the case when you have ceramic to metal bonding. So that poses some additional challenges. Mostly in this talk, I'm going to look at the wettability problem, but let us first look at the thermoelastic compatibility issues. There are several different ways that people have been using to minimize or manage residual stresses in joints. So we looked at silicon nitride to Inconel 625 system in nickel superalloy. And what we found was that if you directly brazed Inconel to silicon nitride, the bonded region looks fine, but ceramic is fractured because of residual stresses. So stress can be accommodated by the thin brazed layer, and we end up with a crack. And if you try to test this for bond strength, you end up with very, very low strength in the joint. So many people have shown that you can manage stresses using multi-layer. For example, you can put moly tungsten or nickel tungsten or other combinations in this joint region. So you have to select the thickness and the expansion properties. Also, the elastic modulus compatibility should be there. So we came up with these combinations for silicon nitride bonded to Inconel. And this is an example of a braze called copper ABA, which contains basically aluminum, silicon, and titanium. The main constituent is copper. This is a commercial braze commonly used in industry. So you're looking at silicon nitride on this side, copper ABA, tungsten. Then again, you have a layer of copper ABA. Next, we had a molybdenum layer. And then copper ABA, and on this side was silicon Inconel. The Inconel has a very high expansion property, around 17 or 18 at room temperature, ppm per Kelvin. Silicon nitride is pretty low, 3 to 4. So joining them directly will cause a lot of stresses. But when you put these interlayers, you're able to reduce the stress and high bond strength. So in this stress strain plot, to figure out the bond strength, this curve number 2 shows the behavior of silicon nitride to Inconel bonded using moly and tungsten. So compared to very low stresses here for directly bonded joints, we get higher bond strength, about 80 or 90 MPa, which is not very high, but still much higher than what we get in a directly bonded joint. Now, to actually optimize the bond strength, we will need to play with the thickness of these interlayers and other parameters. We haven't done that. We, in fact, focused more on the interface in the system. So this is one way to manage stress by putting interlayers. Another way that we looked at was using a composite braze. And again, a lot of people have worked on this. So instead of directly bonding to substrate using a braze, you could actually create a composite. In this case, we are looking at silicon carbide powders added to a silver, copper, titanium braze, different percentages, and that is used for joining the ceramic. So the advantage here is that by putting silicon carbide in a high expansion braze, you are able to reduce the expansion coefficient of the braze and bring it closer to the bonded surfaces. And the other advantage is that you expect the conductivity to increase. Conductivity of the braze region will go up when you disperse a judiciously selected reinforcement. Of course, in a case of like silicon carbide particles, if you're using an active braze like TiQsil, which is titanium, some of the titanium will be lost in the reaction with the substrate, and some will be used up in reaction with the particles. So you may have to control the amount of titanium in the braze to get the right thickness of the reaction layer. Other things that people have tried is to use a porous interlayer instead of a composite braze or multi-layer. You can use a porous layer and other applications here. Let's see. One of the composite that we looked at was basically a silicon carbide material It's called SA Hex, contains silicon carbide fibers, beta phase, and this is a product of Ube Industries from Japan. And so the fibers they look like this here. These are the basal planes, and then you have the prismatic planes. We bonded this material on both faces. So in some systems, we bonded the basal planes using a braze, and in other cases, we bonded the prismatic planes. So we had two different orientations of the fibers at the mating interface here, and we did some studies on the interaction, phase formation, and all of that. We did not really find any difference in the chemical interaction. The fibers oriented differently. In all cases, we saw titanium silicide and titanium carbide, which is what you expect from the basis of thermodynamics. But the interesting difference was that the stress rupture behavior is different for fibers bonded different orientations. What we found was that the joints where the fibers were parallel to the brazed region, the joint was less sensitive to temperature as compared to when we had fibers perpendicular to the joint interface. And that could potentially be a reason, or it could be due to the low shear strength, interlaminar shear strength of this material. And of course, we are seeing the decrease in lifetime with increasing present temperature, which is what you would expect in a general case. But this was an interesting new thing we found. The orientation of the fibers at the joint region will affect the rupture behavior. So as I said earlier, I'm going to look at the wettability problem a little more detail in this talk today. So what are we considering here? Essentially, wettability in a system controls the reactivity, the formation of the interface, and the bonding or adhesion. So this is a classical area, and people have worked on this for more than 150 years, mostly with low temperature systems, and for the last 60 years or so with high temperature systems also. We know that reactions at the interface or other types of modification of the interface can change the adhesion in between the ceramics and the metals. So here I'm looking at some examples from my early work on fiber reinforced metals. Here is an example of sapphire fiber, single crystal sapphire fibers in a nickel aluminide matrix. And this material was either vacuum induction melt and cast in copper mold, or it was made by powder metallurgy. So this was our starting raw materials in which the fibers were oriented like that. Then we directionally solidified this feed material using a floating zone configuration. And the idea was to grow large columnar grains with the sapphire fibers completely confined within a grain. In other words, if you have very few grain boundaries of the NIL matrix coincident with the fiber, then you expect higher bond strength. I'm sorry, if you had a fewer boundaries coincident with the fiber, you will have higher strength. Because grain boundaries essentially are like micro cracks. So if you can eliminate grain boundaries around the fiber, you should be able to expect very high bond strength. So what we did was we sectioned small wafers of the composite after directional solidification, did microscopy and all that, and we tested the bond strength of the fibers that were confined within the grain and the fibers that were sitting at grain boundaries. And we did fiber push-out test, a lot of these kind of fibers in this kind of a test, and some of you might be familiar with that. It's the precursor to the more recent nano-indentation kind of test. But you essentially slide the fiber out of a thin wafer and record the load versus time or stress strain plot. So what we found was that fibers that were completely engulfed within this grain, they had much higher bond strength than the fibers that were sitting at a few grain boundaries. Our idea was to eventually grow a single crystal NIL matrix with sapphire fibers embedded in it. We also modified the interface in the system using different alloying elements. So I'm showing you the example of how ytterbium, a highly reactive rare earth element, ytterbium, how it modified the interface between the sapphire and the matrix around it, NIL matrix. And when you do the fiber push out to find the bond strength, you see high bond strength. So this kind of a roughened behavior. So the interesting thing here is that reaction can increase the bond strength dramatically, but that may be very beneficial, especially because the fiber itself is heavily degraded. So the composite properties will not improve even though the bond strength has improved. So the idea is that you can modify the interface in different ways to control the bonding or the adhesion. So the question is, why study this kind of a ceramic metal interaction? It's a very old, much researched topic. A lot of experimental work has been done, and there is a large body of knowledge that is currently available on these high temperature systems. The challenge is that most of the work that has been reported in the literature has a lot of scatter because of uncontrolled conditions. There are no standard ASTM or ISO kind of tests for wettability or adhesion. There are some for adhesion and for wettability. So the data are all over the place, and very few high fidelity experiments exist. So in the next slides in this lecture, I'm going to mainly focus on some unique experiments that I did with my Polish colleagues using some very advanced and interesting instrumentation that they built. So here is a high temperature wettability test unit that was designed and fabricated in Dr. Sobczak, Natalia Sobczak's lab. Earlier, she was at Foundry Research Institute, and then recently, about a year and a half ago, she relocated as a professor and head to the Institute of Metallurgy and Materials in Krakow. This is the wettability test unit that can go to 2100 degrees Celsius, and you can do the testing for contact angle and surface tension of the properties, both under non-isothermal and isothermal conditions. The unique feature is that you can manipulate the droplet under high vacuum. You can open the interface between the ceramic and the liquid metal, and you have some other features that can really give you unique perspective. So we use this unit for a few systems, ceramic metal systems, and I'm going to show some of the results in this talk. But first, for a moment, let us go back to the basics of what we are trying to learn here. The concept of a contact angle is very well known. It was put together by Thomas Young, maybe about 130 years ago. So essentially, if you have a liquid droplet in contact with a solid, the liquid droplet might spread or it might ball up. So if you have a teeny drop of mercury on glass, mercury will ball up. But if you have water droplet on a glass slide, a clean glass slide, water will spread out. So the angle that a liquid droplet makes with a solid surface is called the contact angle. And if you want spreading to take place, like a brazed layer to spread out, you want this angle to be nearly zero. Of course, in some applications, you don't want wetting. So for example, in melting crucibles, in foundry work, you don't want the liquid metal to wet the surface of the crucible. But the application that we are looking at, joining the low contact angle is important. One interesting thing here is that in a non-reactive low temperature system, like an organic liquid on a solid surface or even water, on a glass slide, water will take just a fraction of a second, a few milliseconds maybe, to spread out to an equilibrium shape. Not so with high temperature systems. When you have a liquid aluminum sitting on a solid ceramic surface, the droplet can continue to spread for half hour or 1 hour, provided, of course, you control the cooling conditions, the temperature, and other things here. And the reason for that difference in the behavior between temperature systems and high temperature systems is that there's continuous interaction going on between the liquid and the solid that could be modifying the surface ahead of the liquid. So the reaction layer could be spreading ahead of the liquid. It could cause roughening or other changes. This is an example of how evaporation of a liquid droplet under high vacuum would cause condensation of the liquid droplet on the solid surface. So as the droplet spreads, the surface ahead of it is modified. So here is an example of that. We have a nickel droplet on chromium-coated aluminum oxide substrate. And when we did the wetting test, what we found was that the evaporation and condensation of nickel ahead of the spreading droplet could modify the surface. So the droplet is spreading on a previously modified interface. In this particular case, we saw nickel chrome eutectic micro droplets forming on the surface of this alumina substrate. So these kind of challenges do not occur in low temperature systems or non-reactive systems, but they're unique to high temperature systems like molten metals and ceramic materials. Other challenges that are encountered are basically from roughness on the surface or chemical inhomogeneity. The surface of the solid might be chemically inhomogeneous, and that will affect the spreading and the contact angle. In composite materials, especially when you're dealing with ceramic materials, ceramic composite, even after grinding and polishing, the surface is not perfectly smooth. So the spreading droplet may not be completely round. It could be an isotropic spreading, and that makes the measurement of angle of contact challenging. There are a lot of things happening during the spreading of liquid on solid in reactive systems. So in the case of aluminum spreading on carbon, you're actually forming aluminum carbide by a strong exothermic reaction, and the aluminum carbide crystals form ahead of the interaction zone or the liquid spreading liquid. In the case of nickel aluminum on magnesium oxide substrate, we see whiskers of a magnesium aluminate or a spinel whiskers. So the surface is roughened. In aluminum silica, a very common system, there is reaction taking place, you form aluminum oxide, and there is volumetric change that can cause cracking in the substrate. Here you're looking at a movie of how aluminum spreads on aluminum oxide that has a coating of nickel phosphorus. So this is under very controlled condition, and you can see that aluminum will wet a phosphorus plated aluminum oxide surface because you form low contact angle. Look at the next situation here, where you have an oxide film on the liquid droplet. So you can see that oxide skin is very tenacious, and the liquid aluminum is melting underneath and trying to spread out. In this case, if you were not careful enough, you would measure an incorrect contact angle because this oxide skin is preventing the liquid to spread out fully. So in reality, we are looking at aluminum silicon on this coated alumina substrate, and that is wetting the system, wetting the solid surface. But the shape of the droplet tells you that it's a non-wetting system, which is not correct. So the oxide skin on the metal is causing a lot of problems. But under high vacuum and under certain conditions, the oxide can actually dissociate and it can allow for spreading to take place. Let's see here if I can get it to move. You will see the oxide on the droplet breaking apart. You see the pieces of oxide breaking, and the shiny droplet you can see because you can also see the camera, imaging camera uh, on the droplet here. And of course, this is during the cooling process here. This is what you see here. The droplet has oxide which broke off. These kind of experiments are pretty difficult to conduct because you have very high vacuum system and you want really controlled temperatures. So basically, if you look at the data on contact angle of aluminum on the aluminum oxide substrate, you see the results all over the place. So here, contact angle versus temperature in alumina gives you values that can go from less than 90 degrees to over 170 degrees. And that is because the contact angle is extremely sensitive to the substrate condition and also the testing conditions. That is a challenge, but that is also an opportunity because contact angle measurements can serve as high fidelity probe to investigate surface interfaces. So that was the focus of our work, that we wanted to use measurements of contact angle to investigate the best in ceramics and metals. So again, we're looking at the effect of melt oxidation on contact angle. If you have a thin oxide skin, the angle is very large. But if you raise the temperature under vacuum, the angle will drop because the oxide will partially disappear. Typically, above 900, it's not fully sintered, fully dense, so it has some porosity in it. And during the wetting test, you can see that rays has permeated into the pores, but also form a reaction layer. We see the same thing with composite, like carbon-carbon composite, on which we have a brazed droplet sitting. And because of porosity, some of the liquid is wicked in the pores in the carbon composite. When that happens, the volume of the liquid changes, the contact angle changes. Now, generally, when you conduct a wetting test using the so-called sessile drop method, this is what you do. You put the solid metal in contact with the ceramic in a vacuum chamber, go for multiple purging. So you evacuate and backfill with argon, again evacuate, backfill, do it multiple times until you have a relatively clean atmosphere, and then you heat the system until the droplet melts, and you allow it to spread out until you get an equilibrium situation. So this is what is happening during what we call contact heating, CA. The problem is that if you want to investigate the interaction really scientifically between liquid and solid, this approach is not good because during heating in the solid state, there are reactions taking place, not just between the liquid and the solid. So a better method that's used is the so-called capillary purification, where you squeeze out the liquid metal out of a capillary made out of either high purity aluminum oxide or sometimes graphite. So you melt the metal separately, you heat the substrate separately, and when the temperatures are right, you squeeze a droplet and bring it in contact with the substrate. When that happens, you can actually time the spreading of the droplet. You can control the time for interaction between the liquid and the solid. So this was one approach we used using Dr. Sobchak's setup. And here you're looking at that example of squeezing aluminum droplet on a silica substrate. So what is happening here is that because of squeezing action, you are able to erode or remove the oxide skin on the surface of the droplet. And the droplet can spread out and give you good wetting in a braze or other type of systems. If you did this kind of an experiment using contact heating, you will get poor wetting. So if you look at the contact angle versus time results for aluminum and silica, this is what you see. With contact heating, you need to go to 1273 Kelvin in order to get low contact angle. But if you use the capillary purification, squeezing out the liquid from the capillary, that approach, then you get very low contact angle, comparable angles even at 973 Kelvin. So this clearly shows that the oxide is what is causing the problem here. The same thing happens with alumina system. We are looking at contact angle time data at different temperatures for aluminum, pure aluminum and aluminum oxide. And what you see here is that the angle is very large at low temperatures, and the angle drops below 90 degrees only when the temperatures are very high, 1200 or 1300 Kelvin. But you can achieve relatively low angles by the capillary purification approach even at low temperatures. We did some bond strength measurements for studying the effect of wettability on adhesion. So we looked at aluminum titania and also aluminum zirconia system. These are the wetting data, contact angle versus time at different temperatures for these two ceramics. And these are the corresponding bond strength data. So aluminum titania and aluminum zirconia after wetting test at these different temperatures. This is how we measured the bond strength. In wettable system, the liquid can spread out quite a bit. So pushing the droplet sideways is not very helpful, especially if the droplet is very thin. So we use this bisectioning approach. We would bisect the droplet substrate combination after cooling, and then use the shear test to slide off one half of the droplet. So what you're seeing here is, again, the effect of temperature. If you were using capillary purification method, that is squeezing a droplet out of the capillary and then contacting the alumina or titanium substrate, you would see very high bond strength even at a temperature like 1173 Kelvin. If you do contact heating and then do the bonding test, the graph is somewhere here. So again, this is because you are able to remove the surface oxide of the droplet. That is why you get high bond strength. We see the same behavior with aluminum zirconia system. This kind of a wettability test has been done on other ceramics, high temperature or ultra high temperature ceramics like zirconium diboride or hafnium diboride. And again, you would see the same kind of behavior with contact heating versus capillary purification. We did some work for composite materials, wetting test on silicon carbide composites. And even though our contact angle, the measurements are not thermodynamic contact angles, they are practical usable contact angles. They are not thermodynamic angles mainly because of the surface roughness effect and anisotropic spreading. But from a brazing standpoint, these angles tell us which braze would be a suitable one for joining ceramic to metal or ceramic composite to metal. We also do a droplet suction kind of an approach where you have a droplet first in contact with the solid, and then you will actually suck it to open up the interface after a fixed amount of time. So you will see the droplet being removed to open up the surface here. So this allows a very controlled amount of time for interaction of the surface, and that can be examined after cooling using analytical microscopy and the methods. So droplet suction was also used for some of our systems. One other thing we tried was droplet pushing. So if you have contact heating process, you start with a solid metal on solid ceramic substrate, let it melt, and then mechanically you push the droplet from one region to another region and open up this interface. You can do the same thing with capillary purification, squeeze out the liquid, and after a set amount of time, you can push the droplet from one region to another region and open up the interface. We also did this kind of a thing where we had contact heating on one type of substrate, for example, magnesium oxide and nickel here. And then after melting, we could actually slide the droplet from one substrate to another substrate. So a lot of these things are possible because of sophisticated instrumentation and very controlled conditions. So here you're looking at pushing of the droplet. So initially, when you push this droplet, let me just repeat this one again. You're pushing this droplet, but it's coming back. So there are two things happening here. We have a magnesium oxide. This should be MgO 100, and then underneath you have aluminum oxide. So initially, when you try to push, the droplet wants to come back to magnesium oxide. It doesn't slide up on the aluminum oxide. Even though the system that we are looking at, nickel tungsten on magnesium oxide, that's a non-reactive system. But even then, the droplet doesn't want to leave magnesium oxide because the wetting is good, even though it's not a reactive system. So this kind of pushing of liquid is possible with this kind of instrumentation. And after you push the liquid away, you can look at the interface underneath the droplet. So over here, this is the AFM image for magnesium oxide under nickel tungsten. So this is the droplet that was removed, and this is the original surface of the substrate. This is the triple line on the contact region, the boundary of the liquid spreading on the MgO substrate. This is under the droplet. And essentially what you see, after you open up the interface, you have very teeny microscopic droplets sitting inside dislocation edge pits. So after you slide the droplet away, it still breaks up into teeny particles or liquid droplets that continue to reside on the surface. You're not able to push the whole droplet away, which shows that there is some wetting in the system here. So again, this kind of an experiment is possible because of sophisticated instrumentation available. We are looking at commercial purity aluminum on polycrystalline and single crystalline aluminum oxide, polycrystal substrate, single crystal substrate, and pure aluminum. You're pushing the droplet, opening up the interface. So you're looking from the top, on the opened interface here, and you see aluminum oxide crystals even when you have a single crystalline substrate. And these things form because of the dissolution of the ceramic in the droplet and reprecipitation of aluminum oxide crystals during cooling. We see the same thing with single crystal and also with polycrystalline aluminum oxide. You have new aluminum oxide crystal forming under the droplet because of dissolution reprecipitation. Other things that we have tried are rotating the substrate while squeezing the liquid you can actually shear the liquid in contact with the substrate and examine the behavior, or you can transfer the droplet from one substrate to another. These things are easy to do for low temperature systems, water or organic, but very hard to do for high temperature systems. Let's see, how much time do I have here? It's almost what, 6:24. How many minutes do I have?
How much time you require? Whatever you require, you can continue.
Okay, I will take maybe just a few more minutes here, just quickly wrap up the things. Um, so again, we are looking at some systems where you can have high adhesion, even though wetting is not very good. So in this case, if you see, oops, the liquid is actually pulling up this substrate because the bonding is very good, even though the contact angle that we measured was not very low. So it's a non-wetting system, but high adhesion. Another thing we did was to look at aluminum silica system. We're looking at interaction between the two through the transparent silica plate. And this is the reaction layer that is forming continuously. So the way this experiment was done was like this. We had aluminum oxide substrate, we had a solid aluminum piece sitting on it, and this is the transparent quartz silica plate. And we are viewing the droplet of the solid metal on the liquid from this side here. So you actually see the droplet melting in contact with the silica, and then a reaction layer is forming and becoming larger and larger. And as we know, this is a reactive system. Aluminum silica is a highly reactive system where you form aluminum oxide. And even though you start with pure aluminum in this case, you have silicon leaching out from silica. So the droplet becomes aluminum silicon alloy. And underneath the droplet, you see aluminum oxide crystals from the reaction. We did the same kind of experiment with multiple silica plates, so we could see the reaction and infiltration concurrently. So here, the aluminum droplet is actually permeating and also reacting with the transparent silica plates. And of course, upon cooling, you will see the crack formation. So these are the plates here, and then you have aluminum on the top. Other things we are looking at are basically some interesting things in a system like nickel chrome droplet or magnesium oxide. You see some kind of a fluctuation in contact angle. Basically, the metal droplet will dance and change its contact angle during spreading. And that is because the droplet will interact with magnesium oxide, and it can form really small, teeny microscopic bubbles from reaction. And those bubbles will cause the droplet to change its shape, which shows up like the dancing droplet. So this is not bubble that is entrapped from the atmosphere in the furnace, vacuum furnace. It is actually the bubble that forms from the reaction. And you can see that in this AFM image, where there is a ridge formed around the bubble. The substrate is slightly raised because of action and formation of the bubble. So if I run this movie here, you will see the droplet dancing and causing a slight change in the contact angle. Again, you can see the image of the camera on the shiny droplet. Now you will see the droplet dancing a little bit in a few seconds. This one here. So these are movies, but actually the actual time of spreading is somewhere between 45 minutes to an hour. But the movie shows it as a really rapid thing. So essentially, all these kind of experiments allow us to investigate the interaction between liquids and solids in a lot more detail than would be possible in a traditional system. Just to save time, maybe I can skip some of the slides. Here you're looking at how the volume of a ceramic changes because of chemical reaction. So this solid metal is going to melt, and let's start here from the beginning for a moment here. So initially the ceramic is flat, but see what happens after the interaction. The ceramic will change its volume, and you can observe it in situ. So the droplet is going to begin, the solid metal is going to begin melting, and you can slowly watch how ceramic is increasing its volume. The surface is no longer flat, it is curving because of the reaction. And the reaction product has a larger volume compared to the initial substrate, and that's why you are seeing the expansion of the substrate because of the actual reaction. All right. Yeah. Okay, I will just wrap up here. I'm going to look at basically the summary. What we are seeing is that you can examine ceramic metal interfaces using some interesting new equipment. So even though the area is very, very old, you can have many different complex functions occurring. That is, you can push, smear, or rub the liquid on the surface and examine how uh, the reactions can modify the surface. So this is kind of an ongoing work. Some of it is related to brazing work that is more applied for us, but some of it is more of the basic science kind of an approach. So I think that's pretty much all I wanted to share, and I'll be happy to discuss if anyone has any comments or questions. Thank you for your attention.
Thank you, sir. She was present, but okay. Any question from student? Okay, sir. If anybody having no question, then we can move to next person. Okay. First of all, I wish to thank our eminent guest, Professor Rajiv Asthana, sir, for delivering such beautiful, informative presentation. As we come to the end of the present webinar series, I also wish to thank all the previous guest speakers who delivered the talk in this series. Starting from the technical talk on 19 September 2020 by Professor Kamaniya Chattopadhyay on aluminium superalloys for high strength, high temperature application. Webinar 1 was on the topic of tough high carbon martensite by Professor Harry Bhadesia on 3rd November 2020. The second webinar was on accelerated development of high performance magnetic materials by Dr. Varun Chaudhary on 6th November 2020. The third webinar was on multi-scale and multi-physics simulation on chemomechanical crystal plasticity problems using Damask by Professor Derek Reve on 24th November 2020. The fourth webinar was on processing properties and application of different classes of titanium alloys by Dr. Amit Bhattacharya on 19th December 2020. And today we had the final technical talk by Professor Rajiv Asthana on the topic of ceramic integration using active resin and diffusion bonding. We are very glad to organize this webinar series consisting of talks of diverse technical domains and speakers from leading institutes, universities, organizations all around the globe. I want to thank our beloved head of the department, Professor Madan Mohan Ghosh, who nucleated the idea in my mind for arranging the webinar series under banner of both IIM and NIT Durgapur. I want to appreciate the effort of IIM student chapters committee members of NIT Durgapur for their efforts to organize such events. I also want to acknowledge the support of IIM Kolkata head office and Durgapur local chapter for organizing such kind of technical webinars. I wish to thank the president of IIM Kolkata, Professor A. Gokhale, Mr. L. Badu, Secretary General of Durgapur local chapter, Professor Anupam Basu, Director of NIT Durgapur, Professor Bishwajit Haldar, Dean Student Welfare, NIT Durgapur, for providing us the opportunity to open the IIM Students chapter at NIT Durgapur. This results the flow of knowledge to the students through this kind of knowledge sharing platforms. From the beginning of our new student chapter in 2020, the chapter is in association with the Department of Metallurgical and Materials Engineering had organized total 6 such webinars. The total participant of this webinar series was near about 1450 from more than 19 countries, including India, through MS Team, Facebook Live, and YouTube Live platforms of IIM student chapters. I want to thank all these participants for their active participation to make this event successful. Last but not the least, I want to convey my heartfelt thanks to all the IIM NIT Durgapur student chapter organizing committee members and all the faculty advisor of IIM NIT Durgapur student chapter and faculty members of MME department of NIT Durgapur for making this webinar series possible. We hope we will conduct same kinds of technical or events in this new year 2021. By saying this, I declare the official closing of today's webinar as well as webinar series of the session 2020 to 2021. Wish you all the best and Happy New Year 2021. Thank you.
All right. I want to thank you.
Thank
Dr.
you.
Manju.
Thank you.
Thank you, Dr. Ghosh. It was good to see all of you virtually.
So it is also a nice to have you with this in this kind of program, and we'll be happy to have you in future in other events or programs. And your advice for the progress of the department is very much essential. And I will like to have you in other events or future events. Thank you, sir, for your very nice talk.
Thank you, sir.
Thank you, Dr. Ghosh. I'll be more than happy with you in different ways in the department. So yeah, we'll stay in touch. Okay. All right.
Sure.
Thank you. Thank you again.
Okay. Thank you,
Bye
sir.
now.
Thank you, sir.
Bye.
Bye.
Thank you, sir.